So one of the things that I've done in my life is teach math, like middle school, high school grade level, uh, tutoring, teaching, and that kind of stuff. Yeah, and I have an associate's in mathematics, so I'm relatively competent with at least that level of mathematics up through calculus. Um, One of the things that I've noticed, and I've never seen anybody else talk about this, although if you look in like engineering uh, handbooks and things like that, they'll kind of mention this casually. But pi, the 3.14 thing, that number, I don't think it's the real fundamental circle constant. And at this point, I'm going to mention that no, tau is not what I'm talking about either. 2 pi. Um, yeah. There's another number that you can actually very easily and systematically derive both pi and tau from, that as far as my research into this subject has discovered, nobody seems to have kind of fully recognized, even though they've kind of casually recognized it. Um, I have in my hand a Soviet uh, aeronautical clock from, you know, I don't know what kind of airplane, if this even ever flew, but yeah, I thought this might kind of help illustrate my point. Um, so the way that I think about circles, and this is how I get to my analysis of what the fundamental circle constant should be by thinking about circles, should be obvious, right? Yeah. Um, it's you take you look at how you find the area of other sorts of things, and then you look at how you find the area of a circle. You look at how you find the perimeter of other sorts of things, and then you look at how you would, and then you apply that to find the perimeter of a circle. Weirdly, this isn't how it's classically done. For some reason, the way that it's normally taught, at least, is the way that you find the area of a circle is completely different from how you would find the area of a rectangle or a triangle. And the way that you would find the perimeter of a circle is completely different from the way that you would find the perimeter. Well, or it's talked about as being different from like a square or a rectangle. I'm going to use a square because a circle is a special case of an ellipse, right? It's and just like a square is a special case of a rectangle. So here we got a rectangle. The height is different than the width, right? But with a square, the height and width are the same. With a circle, height and width are the same. So they're kind of the same exact special case. If we uh, if we circumscribe a square around this guy, right? So we've got, kind of do it with my fingers. At least get one corner over here. Um, yeah, you can see like we could treat this as kind of like a physicist looking at things, and just it's a blob, right? If we're looking for the area of a circle, let's first consider the area of the square that it would live in. Right, that square that just fits right around it. So all of its sides just touch at 4 points. Right, the smallest possible square you could fit this circle into. That's what we're looking for. The area of that square turns out to just be, well, it's the area of a square is whatever the side length is times itself, which is why that's called squaring a number, right? Like, so if your square is 4 inches wide, then the area will be 16 square inches, because 4 times 4, or 4 squared, is 16. This is not rocket science, right? With the circle being living in your square, the diameter of your circle, the distance across, that's your side length. So the square that we're looking at is your diameter squared. Normally when we talk about the area of a circle, we look at the radius squared, which is half the width. If we talked about squares this way, you end up with an infinite you end up with a paradox, because you can't, what is the word? Infinite regress. You end up with an infinite regress. Coffee is life. Because what would happen if you're looking for the area of a square this way, and we need to cut the side in half, well, that's going to give you a smaller square. But we don't know how to find the area of a square, so what we're going to do is we're going to have to cut that in half, and we're going to have to cut that in half, and half. And you're never going to get to a point where you can say, yeah, this is the area of the square. You're never going to get to a point where you can build it back up and get the area of the original square. It's an infinite regress. You just keep pushing the problem off one more step, one more step, one more step, one more step. Forever. You can't ever solve it. Now, yes, it's easy to find the area of a square. You just take its side length and multiply by its side length. We know that. That's fine. But the fact that trying to do it in exactly the same way that we normally would do with a circle doesn't work, I feel like that's significant. That actually means something. Anyway, what ends up happening, looking at the quartering thing, so we take our circle, and let's see, let's set the hands, use that to kind of show us. So we've got this square here that we're looking at. Part of it is missing. Part of it you throw it away, right? So we're looking at like the classical way of, so we're taking the r squared, the radius squared. So we're looking at this square here that lives here. It's just at a glance, there should be roughly 4 of them. But we're throwing some of it away, so it's going to be 3 something, probably. That's where pi is coming from. That's why pi is 3 something. Because it's the fraction of 4 that you would get. Yeah. Now, if we look back at the kind of the other way that I was framing it, so we're looking at the square that surrounds this. If we treat it as we're just taking a fraction of the area of the square, and we're just throwing the corners away, like at a glance, it should be kind of obvious that we're taking 3/4, 4/5, something in that ballpark. And that's a fantastic approximation, because the real percentage is pi on 4, which is 0.785 something. I think that's a 3 next. Yeah, 7.85, which is right between 75% and 80%, 3/4 and 4/5, right between there. So this kind of gives you 2 easy approximations, way easier than what 22/7 for pi. Because 7ths are annoying especially with a calculator. 7ths are annoying to handle. Yeah, 22/7 is a closer approximation of pi than 3/4 is to pi on 4. But 3/4, anybody who's handled American money understands what 3/4 is. It's 0.75. Or 80%, like, okay, 8 dimes. And because I live in the US and my students are in the US, handling at least small amounts of money, that's a familiar thing. It's a much easier way to teach it. Also, you don't end up with that weird paradox, that infinite regress paradox, if you look at it this way. Because now what we can do is, okay, so we have some circle constant, pi on 4, 0.785. But we also have a triangle constant, so, that would be 1/2. You take a rectangle and you just cut it corner to corner. That's a half. So we have a triangle constant, and a circle constant, and a square constant is just 1. Right? Very nice. Okay. Does this come up elsewhere? Yes, it actually does. It actually does. Because, so pi on 4 describes the portion of the square that we get for the area, but it also describes the relative size of the perimeter of the circle to the perimeter of the square. So we have a number, yeah, so the circumference of a circle, the perimeter of a circle, the circumference is pi on 4 of the perimeter of the square. So if you have a unit square, it's, one side is 1. You walk all the way around it, you've gone 4, because there's 4 sides. If you put a circle in that fit exactly in that square, and you walked around it, you would have gone pi. But what that means is the ratio of the circumference to the perimeter of the square is pi on 4. The exact same relationship that we have from the areas between these two shapes. And the fact that we have a single number that is telling us about the perimeter of a circle relative to the square it's embedded in, and the area of that same circle and that same square, well, really it's any ellipse and the rectangle it's embedded in. The fact that we have one constant that's handling both a linear value and a square value, an area value, that's kind of amazing. Because normally 1 is the only thing that does that. And even then, yeah, so, and this works for all sizes of ellipse, all relative eccentricities, yeah, all sorts of, all of the ellipses relative to the rectangle that they're embedded in. Also, there's some more magic to this. So we have pi on 4, trumping pi in that it relates a length and an area across all ellipses and the rectangles they live in. But we also see it in a few other places. So if we go out to, let's see, not this. If we go to pi on 4 radians, so say this was 0 degrees, or 0 radians, and this is pi on 4 radians, I understand it's, there you go, like that. The fact is that whew, I can't see this. Okay, so that arc would be pi on 4 radians. That angle. The this distance here relative to, so if we drop our square back on, you can kind of see that minute hand would extend up to that point if everything was perfectly accurate. Right, it would cut 1/8, a triangle that's 1/8 of the area of the square. This distance and this distance, the relationship between them, this is pi on 4 of this. And that goes all the way around. So you can take a circle embedded in a square, cut it in half, and you still have ignoring the new edge that you got from the cut, the part that's original, you still have that relationship of pi on 4 Right, where this is pi on 4 of that part. We can cut it in half again, and you still get that arc is, the distance of that arc is pi on 4 of the two sides. And we can cut it in half one more time, and that little arc of the angle pi on 4 is pi on 4 of that last little edge of the original square. So it goes all the way down, and it goes all the way down to the angle pi on 4. And this is interesting because we also get a symmetry in all of the trigonometric functions at pi on 4, where the prefix co basically means reflect across pi on 4. And you can kind of see this. If you've gotten into trigonometry, you can kind of see this, right? So, like, up to 45 degrees, cosine and sine don't really look like each other. At 45 degrees, they look exactly the same, and then past 45 degrees, they kind of flip roles. All of the trig functions do this. So the cosine, you can think of it as, the cosine is the sine reflected across pi on 4. And the cotangent is the tangent reflected across pi on 4. And the cosecant is the secant reflected across pi on 4. So we have this fundamental thing in trigonometry that's repeating, and we have a specific little word for it, this prefix co. And as far as I can see, nobody has ever defined it this way. If somebody has, then it's just, I also, stumbled across it independently of them, because I'm unaware of anybody saying this. Yeah. But now we can also see, okay, so we've got this pi on 4 thing going. If we doubled it, we would get pi on 2. If we doubled that, we would get pi. If we doubled that, we would get tau. So this is how you get a systematic way to grow this out. And these are all of the symmetries of a square. Right? All of the symmetries of the circle embedded in the square are represented here. With the base, the most basic piece that's tessellated to produce the whole thing being pi on 4. The fundamental piece that's building everything else has an angle of pi on 4, and the relationships area. Oh yeah, so also these little sections that we're making, the area of the part of the circle to the area of the part of the square is also pi on 4. So the area relationship is preserved. The distance relationship is preserved, and that angle, it's named after that relationship. We just don't talk about it as being, So the angle pi on 4 is actually named after this fact, which I don't think this fact was ever recognized. Except that in in like little engineer, I have several of them that do this. There's little tables for looking up relationships for engineers. They will tell you, yeah, the circle is pi on 4 of the square that it lives in, and the triangle is 1/2 of the square that it lives in, and the pentagon is some other thing, and it's super handy because you can just figure out the square, and then you take this portion of it. It's beautiful. It's beautiful. And I think this is actually the correct way to think about this, which means that pi on 4 is the true fundamental circle constant. And pi and tau. And I have seen historic claims, I think it was in the 1800s or so, maybe early 1900s, of somebody kind of coming along and saying, hey, pi on 2 should really be our fundamental circle constant. Kind of like tau came along and somebody was like, oh, wait, 2 pi, because it describes the whole circle. And there's, that's a fair argument in a lot of ways. But pi on 4 gives you all of them. And explains why all of them have really nice properties. And it's also going to be transcendental. It's going to have all of the properties that pi has. It's just more fundamental than pi is. So it's, it's not like using pi is wrong. It's just, it's not the most right, I think. Anyway.